Alright, so in this video we are going to be doing some final review for Calculus 2. Okay, so a couple things before we start here. This review video is going to consist of 30 questions, just drawing from all topics. For each problem, definitely try it yourself first. Okay, you can get a feel of what part of the problem you're struggling on in particular. Okay, and I'm going to go through it right after you try it. So, you can see if you happen to get it wrong, which hopefully you don't, but if you do, you'll see where you got it wrong and you'll see how to correct that. There's also going to be a 100 question video linked in the description. Okay, so if you want some more review after these 30 questions, this 100 question video is an extended version of this Calc 2 final review. Okay, I'm able to draw more questions per topic. So if that's something that interests you, if you really want a ton of review, I really encourage you to check that out. Lastly, if you've been watching my Calc 2 videos, if they've really been helping you, I would really appreciate it if you could consider supporting me on Patreon. It would definitely really help out, and yeah, I would definitely appreciate it. So on to the first question. So for our first question, we want to find the area bounded by the curves y equals 1 over x, y equals x, y equals 1/4 x, and that's all for x greater than 0. Okay, so the first thing we need to do is obviously get an idea of what we're looking at here. We need to graph this. Okay, so let's graph our y equals 1 over x first. That will just look like that, right? Okay, and make sure you label it so you're not integrating the wrong thing when we actually have to go integrate later. Next we have y equals x. We know what that looks like, all right? And I'm only drawing this for x is greater than 0. Honestly, you could just kind of forget about this whole part right here. So we have y equals x. And then y equals 1/4 x is just going to be y equals x, but not as steep. All right, so that's y equals 1/4 x. Okay, so now what area are we talking about here? What's that region bounded by the curves? Well, that's right here, okay? That's this region right in here. That's being bounded by all the curves, okay? It's important that you that you identify the right region, okay? Because if you don't, if you're trying to find something like this right here, that's going to throw you off completely. So now we need to figure out how we're going to actually find the area, okay? And of course, we're going to have to integrate. Now, what you'll notice is that we have two separate top functions, okay? When we integrate between two curves, we have a top function and a bottom function, okay? But here, we have two separate top functions. We have x at first, and then we have 1 over x at this. That's going to happen at that intersection point right there, okay? That's where it switches over. So what we're going to have to do is we can set up two separate integrals, and the first integral will be from, we know it's going to start at 0, okay? It's going to start at 0. We don't know where this intersection point is, so we got to figure that out. But what is going to be our integrand? Well, that's just going to be the top function minus the bottom function. Okay, the top function being x, and the bottom function being 1/4 x. So this will be x minus 1/4 x dx. Okay. Now, what is going to be that intersection point? Well, what we can do is we can set x equal to 1 over x, okay? Why are we doing that? Well, we want to figure out where x crosses 1 over x, okay? That's the idea. So, obviously here, x squared equals 1, and we can take the square root of both sides. X is going to equal plus or minus 1, okay? And we're dealing with positive x's here, so x is going to equal 1. So that is our top bound, okay? So that's your first integral. Now the next is going to be from, well, you're going to start off at that 1, and you need to find this intersection point here, what the x value is there, and that's going to give you your top bound. But what is your integrand? Okay, well, your top function now is 1 over x, so you're going to start off with 1 over x, and then you're going to subtract your bottom function, which in this case is still 1/4 x. Okay, now we can find that top bound by setting 1/4 x equal to 1 over x. So 1 over 4x, you can write that as x over 4 is equal to 1 over x. Now, we can move things diagonally when it's two fractions equal to each other. Okay, so this x can come up here, this 4 can go up here. Okay, and you can just multiply on both sides if you want to see that. Okay, it's basically cross multiplication. We get that x squared equals 4. Okay, take the square root of both sides. X equals plus or minus 2, but we don't care about the negative, we care about the positive. So, x equals 2. That is our top bound. Now before we integrate here, what we can do is simplify this down a little bit. So we have the integral from 0 to 1 of this is just, well, this is a x minus a 1/4 x, which is just a 3 over 4 x. Okay, multiply by 4 over 4 here and you'll see what I'm talking about if that didn't make perfect sense. Now, our next, we have this integral from 1 to 2. We don't need to simplify this at all. Okay, this will be easier to integrate by itself. Now, when you integrate here, you're going to get, well, this power will get raised to a 2, and then we'll divide by 2. So we'll be getting a 3 over 8 x squared, and that'll be evaluated from 0 to 1. And then we have plus, we'll do this in parentheses here. This will be the integral of 1 over x is a natural log absolute value of x. We're only dealing with positive x's in our bounds, so we don't really need to worry about that absolute value. So we can just write natural log of x. Next, we'll have a minus, well, the integral of 1/4 x is going to be x squared over 8. Or 1 over 8 times x squared. If that sounds better to you, then this will be evaluated from 1 to 2. Okay, so now just doing our evaluation step here, our 0 is going to kill this off. Okay, so we don't need to worry about the 0 at all. We're just going to have a 3/8 times 1 squared, which is just going to be 1, but we'll write it anyway. And then we'll have over here a natural log of 2 minus 2 squared, which is going to be 4. 4 over 8 is 1/2. Okay, and that will be a minus a natural log of 1, which is 0. Okay, and that'll be minus a 1 squared, which is 1 over 8. Okay, so simplifying this a little bit, you get a 3/8 plus a natural log of 2 minus a 1/2. You can see that we have over 8s here. Okay, so we're just going to make this 1/2 a 4 over 8. So we'll have minus 4 over 8, and this will become plus plus, and you have plus 1/8. Okay, simplifying this down a little bit more, just combining your like terms here, you have 3/8 plus 1/8, which is going to be 4/8, and then you have minus 4/8. So that's going to go away, and you're just left with natural log of 2. All right, so one problem down, 29 to go. All right, so question number 2, we want to find the volume of the solid obtained by revolving the region bounded by y equals 1 over x, y equals 0, x equals 1, and x equals 4 about the x-axis. Okay, so let's get an idea of what we're looking at here. We have this region bounded by these 4 curves here. Okay, so we can graph that. Okay, we have 1 over x. We have y equals 0, which is going to be this line right here. We have x equals 1. And we have x equals 4. So that's going to be, we're talking about this region right here in blue. I'll color that in blue. Okay, and we're revolving that region about the x-axis. Okay, now the x-axis, of course, that's right here. So when we rotate it, okay, we get, so you can see here, if you were to slice this solid this way, your cross sections would be circles. And we know that the area of a circle is pi r squared. Okay, now if we want to find the volume of this solid, what we're going to do is add up all of these cross-sectional areas. Okay, and how do we do that? Well, we take an integral. Okay, we integrate pi r squared. okay? And, well, how do we go about doing that? Well, our bounds are going to be from 1 to 4, okay? And your radius, well, that's the distance from, let me get this blue out of the way and write your radius. Your radius is from your curve to the axis of rotation, okay? So that is r. Now, we know that the radius is 1 over x, okay? The distance from this curve, 1 over x, to the x-axis is 1 over x, okay? So what we're going to now have here is we're going to replace this r with 1 over x, and that's going to be getting squared, okay? So we can pull this pi out, and of course we're going to have a dx on the end here. We're going to pull this pi out, and then we have the integral from 1 to 4 of, this will now be a 1 over x squared dx, okay? Now when you integrate 1 over x squared, what you get is negative 1 over x, and that will be evaluated from 1 to 4, okay? So now doing that, you get that volume is equal to pi times, this will be a negative 1/4, okay, and that will be minus a negative 1 over 1. Okay, so that's basically negative 1/4 plus 1, which will be 3/4. So your answer is going to be that your volume equals 3 pi over 4. So just to recap here, we started off by graphing what they gave us and rotating about the x-axis. Okay, now we know that if we cut this solid this way, our area our cross sections are going to be circles, and the area of that is pi r squared. Okay, so if we want to find the volume, we add up all of those cross sectional areas. Okay, and we do that by integrating. So we integrated, we integrated, we evaluated, and we found our answer. Okay, so as simple as that. So question number 3 says we need to use the shell method to find the volume of the solid obtained by rotating the region bounded by y equals x squared and y equals 4x minus x squared about the line x equals 4. Okay, so first you need to recall what the shell method actually says. Okay, the formula for the shell method says that your volume, I'm on the wrong side here, your volume is going to be equal to the integral from a to b of your circumference, okay, so it'll be your circumference times your height times your width, okay? And we're getting these because, remember, by shell method, we're talking about cylindrical shells, okay? So we're basically finding the volume of a cylinder here. That's kind of where this whole concept comes from, okay? So this is the formula for the shell method. Now let's see what our region is. Let's rotate it about the line x equals 4 and just get a better picture of what we're doing here. So first we have the graph y equals x squared. Okay, now this is something that we know what that looks like. Okay, y equals x squared. Now next we have y equals 4x minus x squared. Okay, now if you don't know what that graph looks like, because I don't know what that graph looks like off the top of my head, you can just find the zeros. Okay, there's a negative x squared here, so you know it's going to be an upside down parabola, but just find the zeros by setting y equal to 0, you know, just like in algebra, and figuring out what x values will make this y 0. Okay, so let's just do that here. Take out an x, we have 4 minus x left, so you know that the zeros are going to be x equals 0 and x equals 4. Okay, so if those are our zeros, say right here and right here, okay, this graph will look like this. And we're rotating up at the line x equals 4. Okay, so what we're going to get here is just this line coming down, and that's what we're rotating over. All right, now remember, it's bounded by those two curves. Okay, that's what a region is. So that region that we're talking about here is right here. Okay, color in blue for a second. Okay, and we're rotating that around this line. Okay, so now we're going to have to set up our integral. And the first thing, are we going to be integrating with respect to x or with respect to y? Well, remember, with cylindrical shells, we are going to be cutting parallel to the axis of rotation, okay? But with disc method, with washer method, it's perpendicular. So here, all right, our cuts are going to look like this, okay? And that's obviously integrating with respect to x. Think of Riemann sums, okay? So now let's set this up. We have the volume equaling the integral from what to what? We know it starts at 0, but where does our region end? It ends at the intersection of x squared and 4x minus x squared. So what we need to do is set these equal to each other. Okay, so we can say that x squared equals 4x minus x squared. Okay, we can just subtract x squared on both sides, and we get that 0 is equal to 4x minus 2x squared. We can factor out an x here. Actually, we can factor out a 2x here to get that 0 equals 2x times a 2 minus x. Okay, so obviously they intersect at x equals 0. That's one of our endpoints. Okay, and the other is 2 minus x equals 0, which is just going to be x equals 2. So that's going to be our other bound, is x equals 2. So let's get on with it here. First, we have our circumference. Our circumference is 2 pi times r. Okay, what's going to be our radius? Okay, well, think of this. This is a cylinder. When we rotate it around this line x equals 4, our radius is going to be from our solid to our line of rotation. Okay, and well, we know that if we want to find the distance of that line, our radius, we can say that the whole distance from from x equals 0 to x equals 4 is 4. Okay, and then we can subtract this distance from the y-axis to that exact same point, and that's just going to be x, right? That's just going to be x. Okay, that's the distance that you've went over on the x-axis. So right here, you're going to write 4 minus x. Next, we need to figure out the height, okay? So just the height of each of our shells, okay? Now, we're talking about this distance from our top curve to our bottom curve. So what do? Well, we subtract the bottom curve from the top curve. Our top curve is 4x minus x squared, okay? So we'll have a 4x minus x squared here, and that's going to be minus our bottom curve, which is x squared. So we're going to have an x squared here. Okay, and then we have to do our width. Our width is just dx or dy, whatever variable we're integrating with, and that is, of course, going to be an x. Okay, so now let's simplify this down a little bit so we can integrate. We have the integral from 0 to 2. We can actually pull that 2 pi out, so why don't we go ahead and do that? Okay, and now we have just a 4 minus x times a 4x minus 2x squared dx. Now distributing here, we're going to get that this is the volume of 2 pi, the integral from 0 to 2, of, this will now be a 16x minus a 4x squared minus 8x squared plus 2x cubed. Okay, and of course we'll have a dx on the end, but we can simplify these like terms here to get minus 12x squared plus 2x cubed, and we'll have dx. Okay, so now we can just integrate. And when we integrate here, we get that the volume is equal to 2 pi times, this will be, just doing this really quick here for time's sake, 8x minus 4x cubed plus x to the 4th over 2, and that will be evaluated from 0 to 2. So doing our evaluation step here, we get that 0 will kill everything off, so let's just worry about 2. We get 2 pi times 8 times 2 is 16, 4 times 2 cubed. 2 cubed is 8, okay, times 4 is 32. Oh, actually, this is an 8x squared. I apologize. 8x squared, so we'll actually get a 32 here. Okay, great. So now we have a plus x to the 4th over 2, x to the 4th. Okay, 2 to the 4th is going to be 16, divided by 2 is going to be 8. Okay, so we get that this is all equal to 16 pi. All right. So question number 4, what is the average value of f of x equals cosine to the 4th of x times sine x on the interval from 0 to pi? So the first thing you need to know before you start off here is that the average value of a function is equal to 1 over b minus a. Okay, so in this case it would be pi minus 0. Okay, a is the first endpoint and b is the second. And that's the integral from a to b of f of x dx. Okay, so let's just do this here. We get that the average value is going to be equal to 1 over, like I said, pi minus 0, so that'll be 1 over pi. And that'll be the integral from 0 to pi of f of x. That's going to be cosine to the 4th of x times sine x dx. Okay, this is just going to be a simple u substitution here. We'll set u equal to cosine of x, and that means that du will equal sine x dx. We also need to worry about our endpoints here. We have x equals 0 and x equals pi. When x equals 0, u will equal what? Well, cosine of 0, okay, we just plug that in here. Cosine of 0 is 1, so our u is 1. And x equals pi, that's our other endpoint. Okay, and well, that'll make cosine of pi is negative 1, so that gives us u equals negative 1. Okay, and oops, seem to have missed a negative here. Negative sine of x dx. Man, all right. So now we get this is equal to, since we have a negative sine x here, this will be a negative 1 over pi. And this is the integral now from 1 to negative 1 of u to the 4th du. Okay, now since our bounds are going from, it's 1 to negative 1, and it looks a little bit better if we switch it back. And what we have to do then is negate this integral. So if we negate it, this negative goes away on the outside. We get this is equal to 1 over pi, the integral from negative 1 to 1 of u to the 4th du. Okay, and moving further, this is equal to 1 over pi times u to the 5th over 5, evaluated from negative 1 to 1. Okay, so you can now say that this is 1 over pi times, we'll just have a, plugging in 1 first, 1/5 minus a be negative 1/5. Okay, which is just a 1/5 plus 1/5, and that's equal to 2 over 5 pi. Okay, so there you go, that's your average value. Now a quick note here, I wouldn't assume symmetry unless you're absolutely certain there is symmetry. Okay, so when we're integrating from negative 1 to 1, okay, with u to the 4th, we know that there's symmetry. Okay, don't worry about what there is with x's. Okay, then we have different bounds. Okay, when we're integrating from negative 1 to 1 of u to the 4th du, we know there's symmetry, so we could have just said that this was the same thing as the integral of 2 over pi times the integral from 0 to 1 of u to the 4th du. Now you can do that if you're absolutely certain that there is symmetry. I've ran into cases in Calc 2 where I wasn't sure if there was symmetry, okay, and I always just made sure that I didn't go with it, okay. I was just like, okay, let's leave it as it is. I'm not going to change it to something that I don't know if there is symmetry or not, okay. So just a little tip there. Now our next question is we want to integrate from 0 to 1 e to the x times sine x dx. Okay, and you can see here I kind of already spoiled it by putting it over here, but we're going to have to do integration by parts here. Okay, we have two functions being multiplied together, and that's literally screaming integration by parts. Okay, there's no any Calc 1 integral that we can do here. We're going to have to do some integration by parts. Okay, now we have the formula right up here. We have to choose a u and we have to choose a dv. Okay, that's how integration by parts works. So let's say that there's nothing really clear that we can see here of what will make one eliminate the other, and you're going to see that's not even going to be the case. We can't eliminate sine of x, we can't eliminate e to the x. So let's set u equal to sine of x, okay, and du will now be cosine of x dx. Okay, and we'll let dv equal e to the x dx, okay, and v equal e to the x. Okay, so let's see what happens now. Well, we have that this integral is going to be equal to u times v. Okay, u times v is e to the x sine x, and it'll be evaluated on the same bounds. Okay, you don't need to change your bounds at all. Okay, this isn't a u substitution. Okay, this is just kind of, and I know we're setting u equal to something, but with integration by parts, it's different. Okay, you keep your bounds. Okay, we're not changing anything. We're still integrating with respect to x. Now this is minus the integral from 0 to 1 of v du, and v du is e to the x cosine x. And we'll have a dx there. And you see that we're left with pretty much the same exact thing. We have to do integration by parts again. So let's get on with it. Let's set u equal to cosine x. Okay, and du will now be negative sine of x dx. If we set u equal to cosine x, then dv needs to be e to the x dx, basically what's left of that integral. So that would mean that our v, okay, we have to integrate here, and we get e to the x. All right, so now writing this out, we get that this is equal to still e to the x times sine x, evaluated from 0 to 1, okay, minus u times v, so now our u is cosine x, and we have e to the x, so e to the x cosine x, evaluated from 0 to 1, minus the integral from 0 to 1 of v du, and that's a negative sine x dx, okay, times, and of course times e to the x. So e to the x sine x dx. Now you might be saying here, oh my god, you know, we're stuck again, we have e to the x sine x, but that's good, okay? Because if we had this integral back, well, remember what we started off with. Of course, we had that the integral from 0 to 1 of e to the x sine x dx, okay? And what that means is we can add that on both sides. If we add this integral over, okay? If we add this integral over, then what we now get is that we have 2, the integral from 0 to 1 of e to the x sine x dx, is going to be equal to e to the x sine x, evaluated from 0 to 1, minus e to the x cosine x, evaluated from 0 to 1. Okay, so now this is just evaluating, but remember, we're solving for the integral of e to the x sine x dx, not to the integral of e to the x sine x dx. So what we need to do is divide by 2 here. Okay, and just for the sake of not writing this whole thing out again, I'm just going to erase this piece right here. And yeah. Okay, so let's do that evaluation step. We get that our integral is equal to, well, e to the x times sine x. The 0, that will kill everything off because it'll make sine of 0 is 0. Okay, so we just have to worry about plugging in 1. And we get e times sine of 1. Okay, and next we'll have minus. We'll have, well, will 0 kill everything off here? No, because cosine of 0 is 1, and e to the 0 is 1. So we'll need to do both terms. We'll need to plug in 1 and then plug in 0. So plugging in 1, we get e times cosine of 1. Okay, and then we'll have minus, well, like we said, this e to the 0 is 1, cosine of 0 is 1, so this will just be a 1 here. Okay, so, and of course this is over 2, so we'll just multiply this by 1/2. So we get that this is finally equal to, this will be a 1/2 times e sine of 1 minus e cosine of 1 plus 1. Okay, it's plus 1 now because we had to distribute that negative 1. Okay, so yeah. Also, one thing here before I erase the rest, okay, when you are integrating by parts the second time for something like this, where you're not going to eliminate the e to the x, you're not going to eliminate the sine of x, okay? When you have something like that, you can't just now pick your u as e to the x. Okay, if you pick your u as e to the x instead of that trig function that you were picking it as, then everything kind of goes south from there, okay? So you don't want to do that. So next we have the integral of sine to the fifth of x times cosine squared x dx, okay? Now this is a trigonometric integral, okay? This is not going to be a simple u substitution, at least not at first, okay? Because if we set u equal to sine of x, well then du is cosine of x dx, and we're left with that extra cosine of x there. So what we have to do is look at, okay, how can we end up doing a u substitution here, okay? Well, we have an odd power on our sine, so what we can do is say that this is the integral of sine to the fourth of x times cosine of squared x times sine x dx. Okay? And now you have, if you set your u equal to cosine x, okay, set your u equal to cosine x, your du is, this will get canceled out with your du. But there's still the issue that we have this sine to the fourth of x here. So what we do is we use our trig identity that cosine squared plus sine squared equals 1. So sine to the fourth of x is going to equal 1 minus cosine squared of x, and that's going to be squared. Okay? And then we're going to multiply by cosine squared x, and we'll have sine x dx. Okay? So now we can do our u substitution with what I just said. U is going to equal cosine x, and du will equal negative sine of x dx. Alright? So, of course, we don't have that negative to spare out here, so what's going to happen is that we're going to have negative the integral of, this will now be a 1 minus u squared, quantity squared, times u squared. And then we'll have a du here. Okay? So doing a little bit of foiling, and then we'll do a little bit of distributing in the next step, but we'll have a 1 minus 2u squared plus u to the fourth, and that will be times u squared du. Okay? We can distribute through that u squared, and we get a u squared minus 2u to the fourth plus u to the sixth du. Alright? And we can integrate to get a negative u cubed over 3 minus 2u to the fifth over 5 plus u to the seventh over 7, and that will be evaluated. Well, actually, we're not evaluating this one. We're not evaluating this one because this is an indefinite integral. Okay, so now we can distribute through there. We can multiply this negative through, okay, and we can get our u's back to being in terms of x, which is going to be u equals cosine x. That's what we substitute in. So this is going to equal negative cosine cubed of x over 3 plus 2 cosine to the fifth of x over 5 minus a cosine to the seventh of x over 7, and then we're going to add c. There you go. That is your answer. Okay? So we looked at this integral, we saw that it's not going to be an easy u substitution, but we needed to manipulate this to make it a u substitution. Okay? We saw that the sine had the odd power, and what that meant was we could pick off a sine and have that be canceled out with our du. Okay? All that was left to do at that point was to get this sine to the fourth of x in terms of cosine rather than sine, so we could have our u completely replace everything else other than that sine x dx. Okay? Now next what we have here is the integral from x, or it's going to be the integral of x over the square root of x squared plus 4 times dx. Okay? Now, for this integral right here, you're probably thinking, all right, this is going to be an inverse trig substitution. Well, you can do that, and I definitely did that before on a Calc 2 test, and it took so much longer than it had to because this is just a simple u substitution. Okay? Just a u sub. So, and so trust me, I'll always be looking for that now since I messed up like that. Okay, so I don't want you to have to do that, so please just check for a u substitution first. If you set u equal to x squared over, or x squared plus 4 here, you get that du is equal to 2x dx, and you can divide by 2 on both sides to get that du over 2 equals x dx. Okay? You know, so definitely beware of a Calc 1 integral hiding in a Calc 2 test. Now, what we can do here, I guess we'll keep going here, that x dx gets canceled out with the du over 2, so we'll have a 1/2 out here, and we'll have a 1 over rad x squared plus 4 is just going to be rad u, and we can rewrite that since it's 1 over rad u. We'll write that as u to the negative 1/2. And of course we'll have that du here. We already took care of that over 2 by putting it outside the integral. So integrating here, we're going to get 1/2 times, this will be just a, well, we raise 1/2 by 1, which gives us 1/2. We flip it, multiply it, so we get 2 here times u to the 1/2, and that'll be plus c, because this is an indefinite integral. So this goes away, and you're left with rad x squared plus 4 plus c. Okay, so again, I'll say this again because, like, seriously, this will save you so much time on a test if you just check for a u substitution before you do something like an inverse trig substitution, which will most likely take you around 5 to 10 minutes. Now we have our next problem up on the board here, the integral of 1 over x squared times the square root of x squared plus 4 dx. Now this, I mean, you can see that we're not going to be able to do u substitution here, okay? This isn't an integration by parts. It's not just a trig integral where we have to manipulate a little bit and then do a u sub. This is indeed an inverse trig substitution. So what's the substitution? Well, this is, since we have our, we have a plus here, okay, rather than a minus, we know that this is a tangent theta substitution, okay? Now, so we have x equal to a tangent theta. What's a? Well, a is the square root of that number that's attached, which is 2. So we have x equals 2 tangent theta. Okay? If x equals 2 tangent theta, then dx is going to equal 2 secant theta d theta. Sorry, 2 secant squared theta d theta. Okay? So now we have our x and our dx, and we could just go substitute this through right now. The reason why I'm not going to do that is because, well, we have an x squared plus 4 here, and we have an x squared here. Okay, so I'm not gonna rewrite this integral a million times and do step by step by step. What I'm gonna do is just solve for square root of x squared plus 4 and x squared right now. Okay, so x squared, that's gonna equal 4 tangent squared theta. Okay, x squared plus 4 is equal to 4 tangent squared theta plus 4. Okay, and you can factor out that 4 to get a 4 times tangent squared theta plus 1, which is equal to a 4 secant squared theta. Now we have a square root of x squared plus 4. And that means we're taking the square root of this, which is just going to be a 2 secant theta. Okay, so now you see what I mean. We don't have to rewrite this integral a million times. Okay, we can substitute in this x squared, this rad x squared plus 4, and we can substitute in this dx. And that takes care of every single piece that was part of that integral. Okay, so doing that, we get that this is now the integral of, well, dx is 2 secant squared theta d theta. So we'll have a 2 secant squared theta here, and we'll put a d theta out here. This is going to be over x squared is 4 tangent squared theta, and this is going to be multiplied by a 2 secant theta. Okay, so the secant, the squared here will get canceled out with this secant here. So, and this 2 will get canceled out with this 2 here. So we can pull this 1/4 out, and we have 1/4 the integral of secant theta over a not 4, because we already pulled the 4 out. We have a tangent squared theta and a d theta out here. Okay, now looking at this is pretty nasty. We can't do a u substitution. I originally looked at this and I was like, oh, we can just do a u substitution. But we have the squared on the wrong trig function. If the squared was right here, okay, then we could say u is equal to tangent theta, du is equal to secant squared theta d theta. We don't have that. So whatever I do, when I see, you know, some trig functions that it looks really nasty and I don't really know what to do with it, I break it down into sines and cosines. If you break it down into sines and cosines, well, secant theta, that's 1 over cosine theta. And tangent squared theta, that's sine squared theta over cosine squared theta. And we'll have a d theta here. Now this cosine theta gets crossed out with this square here on the bottom cosine theta, and you're left with 1/4 the integral from this cosine will get flipped up. It'll be cosine theta over sine squared theta, and you'll have a d theta here. Okay, and now you can do that u substitution. So what you can do is set u equal to sine x, or sine theta rather. Du will be equal to, now, cosine theta d theta. Okay, and moving on up, you are going to get 1/4 the integral of u to the -2 du. Okay, or 1 over u squared. Okay, so integrating that, you are going to get 1/4 times a -u to the -1, and that will be, we're going to have a plus c here. But we can write this as a -1 over u. Okay, we can do that. And now we need to get this back into terms of x. Okay, because that's what we started off with. Okay, so we're going to have to do that triangle thingy and all that good stuff. So let's start off here. Now, we know that u is equal to sine theta, so we can say that this is -1/4 times 1 over sine theta. Okay, we'll have a plus c here. But we need to get sine theta, okay, in terms of x. We need to get that theta in terms of x. So what we're going to do, set up that triangle, okay, the good old triangle. We know that there, we'll put our angle here, and well, right here, this is telling us that x equals 2 tangent theta. Okay, if x equals 2 tangent theta, then that is the same thing as saying x over 2 equals tangent theta. And we know that tangent theta is equal to opposite over adjacent. Okay, this is our opposite side, this is our adjacent side. So we can write a 2 right here. Okay, now if this is 2 and this is x and this is a right triangle, what is the hypotenuse? Well, the hypotenuse is just going to be the square root of x squared plus 4. Okay, doing a little bit of Pythagorean theorem there. Yeah. So now what do? Well, we have a sine theta here. Okay, and if we express sine theta with this triangle, using that triangle, we can get this in terms of x. So sine theta, we know that sine theta is equal to, well, SOHCAHTOA, opposite over hypotenuse, which is x over the square root of x squared plus 4. So there you go. Now we can get this thing into terms of x with this conversion here, and we get -1/4 times, this will be a 1 over x over rad x squared plus 4, but we can also write this as, well, if this is 1 over, we can say rad x squared plus 4 over x. And then we can write plus c. All right, so, right there, that is your answer. So, make sure that you don't leave it. I've done this myself. Leave it in terms of u rather than convert it back to theta and then to x. Okay, you need to make sure that you do that, or that's going to be some pretty big points off. All right, so yeah. All right, so for our next problem, we have the integral from 0 to 1 of x squared plus x plus 1 over a x plus 1 quantity squared times x plus 2 dx. Now, this is not something that we can do an easy u substitution with. It's not an integration by parts. It's not a trig integral or an inverse trig substitution. This, my friends, is partial fraction decomposition. So, the first thing we need to do is write out our partial fractions. Okay, if we write out our partial fractions here, we're going to get a over x plus 1. This is squared, so the next term is going to be b over x plus 1 quantity squared plus c over x plus 2, and that will be equal to this x squared plus x plus 1 over x plus 1 squared times x plus 2. Now, what do we do next? Well, if we get some common denominators here, okay, for all these, then we can just set the numerators equal to each other. Okay, we can figure out what that a and b and c are. So, here, if we get common denominators, what is the a fraction missing? It's missing a x plus 1, and it's missing an x plus 2. What about the b? Well, the b is missing an x plus 2, and the c is missing an x plus 1 squared. Okay, and we'll set that now equal to x squared plus x plus 1. Okay, we don't need to worry about the denominators anymore because now all of them are the same. Okay, so doing a little bit of distribution here and a little bit of all that good stuff, we get that this is equal to x squared, okay, plus we have a 2x plus 1x, which is going to be a 3x, and then we have plus 2. We have a b x plus, we can write this just as b times x plus 2 for now. We'll leave it. And then we have a c times x squared plus 2x plus 1. And that's going to be equal to x squared plus x plus 1. Okay? So now what we're going to do is we're going to group these. We're going to basically combine like terms here. Okay? Now we'll have an x squared term on this side, and that will just be, we have an a here and a c here, and they're both being multiplied by a singular x squared. So we'll have an a plus c times x squared. Okay? So that's our x squared term. Now we need to do our x term. Well, here, see, we have a 3a, we have a b, and we have a 2c. So we're going to have plus 3a plus b plus 2c, and that will be multiplied by x. Then we need to do just our constant, and that's going to be 2a, okay, so plus a 2a plus 2b plus c, and that's going to be equal to x squared plus x plus 1. Okay, now the coefficient on our x squared term here needs to equal the coefficient on our x squared term here. That means that a plus c is going to equal 1. Okay, and that also means that 3a plus b plus 2c is going to have to equal 1 as well. And 2a plus 2b plus c needs to equal 1, because all of our coefficients here and our constant is all of it is 1. So that's why everything's equal to 1. So now what we can do here, since we already have a 2-variable equation here, we can use these two equations and cancel out the b's to formulate another equation with just a's and c's. Okay, so let's do that. If we take this equation and multiply by 2, okay, we're going to get that we'll get a 6a plus a 2b plus 4c is going to equal 2. And this equation is 2a plus 2b plus c, and that's going to equal 1. So, subtracting these two equations, okay, we get 4a, the two b's go away, and you have a plus 3c, and that's going to equal just 1. Okay, bring this other equation down. We have an a plus c equals 1, but we need to cancel one of these out, okay? And let's get rid of the a, all right? So what we're going to do here is we're going to bring this down, and we're going to multiply it. If we want to cancel out the a, we're going to multiply it by 4. So let me draw a better arrow here. Sure, that'll be x4. So we get a 4a plus 4c, and that's going to be equal to 4. So now we can subtract these, and the 4a's go away. You're left with a negative c equals a negative 3, which means that c equals 3. If c equals 3, that means that a would equal negative 2. If a equals negative 2 and c equals 3, then we can easily plug into one of these equations here to figure out what b will be. Okay, so let's do that. Let's plug into our bottom equation here. We'll get that 2 times negative 2, that's negative 4, plus 2 times, oh well, our b, we don't know that, and our c is plus 3. Get that equal to 1. So negative 4 plus 3, okay, that is negative 1. We add that 1 to the other side, we get that 2b equals 2. Divide 2 on both sides. We get that b is equal to 1. Okay, and now we will be plugging those in up top here and integrating to actually get our answer. So remember, our a was negative 2, so now this is going to be a negative 2. Our b was a 1, and our c was a 3. So now we're going to integrate this, okay? And what we can do is, since these are all separate fractions, we can integrate them separately, okay? So we'll have the integral right over here. The integral from 0 to 1 of negative 2 over x squared plus 1 dx, okay? Which is the same thing as saying put the negative 2 out here and 1 over x plus 1, okay? We have a plus the integral from 0 to 1 of 1 over x squared plus 1 dx, and then we'll have plus the integral from 0 to 1 of, we can pull that 3 out, so we get 3, the integral from 0 to 1 of 1 over x plus 2 dx. Okay? Now this integral is going to be easy, this integral is going to be easy, this integral is going to require a u substitution. Okay? You'll generally not get the nastiest integrals when you break it down like this. Mostly you'll be dealing with probably just like a natural log, or you might have to do a u substitution. Very rarely do I see anything a little more challenging. So you get u equal to x plus 1 here. Du will be equal to dx, and you need to change your endpoints. So what you'll get is, now if x equals 0, u is going to equal 1, and if x equals 1, then u equals 2. Okay, so now we can just kind of do these integrals and then write this integral again. We have negative 2. This will be times natural log of absolute value of x plus 1 evaluated from 0 to 1. We'll have, I'll write this integral next, plus 3 natural log of x plus 2 evaluated from 0 to 1, okay, which means that we can just erase this evaluation and evaluate this whole thing from 0 to 1. Okay, we can do that. And then we're going to add this integral here, the integral from now 1 to 2 of, this is a negative, or sorry, it's going to be a 1 over u squared, which is a u to the negative 2 du. Okay, so this is now, we'll keep this as negative 2 times natural log of x plus 1 plus 3 times natural log of x plus 2 evaluated from 0 to 1 for now. And we will make this, well, this is now a negative u to the negative 1. Or you can write this as negative 1 over u. And that will be evaluated from 1 to 2. Okay, so now let's do our evaluations all together here. And, well, 0, will that kill everything off here? No, it won't, because you'll have a natural log of 1. That'll go away, but you'll have a natural log of 2 here to deal with. So 0 will not kill everything off. 1, let's plug in 1 first. We get a negative 2 natural log of 1 plus 1, which is 2, plus a 3 times natural log of 1 plus 2 is 3. Okay, and this will be minus. Remember, we said this term goes away because you have a 0 plus 1, natural log of 1 is 0, but you do have this 3 natural log of 2. Okay, now we have a plus. This is a negative 1 over 2 minus a negative 1. Okay, when you plug that in. And you're going to add these because it's 2 negatives, and you just get a 1/2 here. So simplifying, you have a negative 2 natural log of 2 minus a 3 natural log of 2, which gives you a negative 5 natural log of 2. You have a plus 3 natural log of 3. And as we said here, you get a 1/2 out of this. And there you go. There's your answer. I believe this was one of the longest problems, if not the longest problem, that we'll be doing in this video, so don't worry. Problems like this are over. So next we want to see, is the function convergent or divergent? We have f of x equal to the integral from 1 to infinity of x over x cubed plus 1 dx. Okay, so we want to see if this integral is going to converge or diverge. Now, is this an integral that we're going to easily be able to do? I mean, we know that since we have this infinity here, we'll have to have a limit as t approaches infinity. Okay, but here's the idea. I mean, this integral is going to be tough. Okay, this integral, I don't even think we'll be able to do it. So what we're going to have to do is look to the comparison theorem. Okay, we can compare x over x cubed plus 1 to, let's get rid of that constant there, let's get rid of that plus 1. Let's compare it to x over x cubed. Okay, because that is equal to 1 over x squared, and that we can do pretty easily. That's an integral that we can do pretty easily. So what's the relationship between these two? Well, since you're adding 1 here, this denominator is going to be larger, so the fraction will be smaller than this fraction here. Okay, so, and of course we should know this by now, this integral will be convergent. So since this is greater than this will be convergent as well. But I'll show you that real quick here. So we have, let's do the, over here, the limit as t approaches infinity, the integral from 1 to t of 1 over x squared dx. Okay, because we should show it. Now, remember, we have to write that limit, okay? We cannot have infinity as a bound, okay? That's something that math people hate. So we have a limit as t approaches infinity, and we just plug in t, which is basically still the same thing as integrating from 1 to infinity. Okay, so now we can just do this integral. We have the limit as t approaches infinity of, integrating this, we get negative 1 over x. Okay, we've done the integral enough in this video. Negative 1 over x, and we're going to evaluate that from 1 to t. Okay, that gives us the limit as t approaches infinity of negative 1 over t plus 1. Now as t approaches infinity, this fraction right here is going to go to 0, and we're just going to have that plus 1, so this equals 1. Now that, since this is a finite answer, this integral converges. Okay, and what that means is that by the comparison theorem, this integral will converge as well. So here's an example of a good written out answer here. We have the integral from 1 to infinity of 1 over x squared dx converges, and it's greater than the integral that we've been working with on the interval from 1 to infinity. Therefore, the function is convergent by the comparison theorem. Okay, that's all you really got to say. Now, in function, you can replace that with this integral if you want. Okay, it doesn't really matter. So because it's asking if the function is convergent or divergent. So, yep. So for our next question here, we want to find the arc length of y equals 1 plus 6 x to the 3 halves on the interval from 0 to 1. Okay, so here we have our arc length formula. Okay, and this is what we need to use for this problem. Okay, so, and remember, this is the arc length formula, not for parametric, not for polar, but for Cartesian. Okay, just for regular Cartesian, no parameter, and we're not talking about polar either. Okay, you know, they each have their different formulas. Now, to use this formula, okay, we know we're integrating from 0 to 1. Okay, that's obvious. So we can write our arc length is equal to the integral from 0 to 1. But what's going to go in this radical? We have a dy dx squared. We need to find dy dx, right? Dy dx is going to equal, bring this 3 halves down, we're going to get, this is 18 over 2, this is 9, x to the 1/2. Okay, and if you square that, okay, if you square that, you get 81x. Okay, so we're going to put an 81x right here. All right, and this just becomes a pretty easy u substitution from here. Okay, so we get u is equal to 1 plus 81x, and du is going to equal 81 dx. Okay, we don't have an 81 just laying around here, so we're going to divide by 81 on both sides. Okay, and also we need to change our bounds. So when x equals 0, what will u equal? Well, u is going to be 1 plus 81 times 0, which is just going to be 1. And x, when x equals 1, u equals 1 plus 81 times 1, which is 82. So we're now integrating from 1 to 82. Okay, so we have the integral from 1 to 82 of rad u times du over 81. So we can write a 1 over 81 out here and a du on the inside. Okay, so going through with this further, okay, this is a u to the 1/2. So when we integrate, this is 1 over 81 times 2/3 times u to the 3 halves, evaluated from 1 to 82. Okay, and well, we have a 2 now. 81 times 3 is 243. And we have a u to the 3 halves, which means we'll have, if you have anything to the 3 halves, what that means is that it's going to be like, if it was u to the 3 halves, it's u rad u. Okay, so for here it'll be 82 rad 82 minus a 1 rad 1, which is just 1. And right there, that is your arc length. Now, what if we wanted to figure out the arc length function starting at this x equals 0? Okay, well, if we wanted to find the arc length function, then all we do is we don't have a top bound anymore. Okay, or we don't have a number in our top bound. Okay, our top bound will become an x. Okay, and it won't be an x here, it'll be an x here, and that will change when we do our u substitution. So instead of an 82, okay, we'll be starting out with x equal to x, and that means u will equal 1 plus 81x. And that will be what we substitute in as our bound right here. So we have a 1 plus 81x. Okay, and then our bound here will be a 1 plus 81x. Okay, and then what we will end up getting, okay, is instead of an 82 rad 82, we'll have a 1 plus 81x to the 3 halves minus 1. Okay, and that will be your arc length function denoted s of x. Okay, so that's all you do for an arc length function. You just put in x in your top bound and you go from there. Okay, and that's going to give you the arc length at any x value. Okay, assuming that you're starting at some x, we're starting at 0 here. Okay. So for our next question, we want to find the surface area of the solid obtained by rotating y equals the square root of 9 minus x squared from 0 to 2 about the x-axis. Now, if we're trying to find the surface area of this solid, we need to use this equation. The integral from a to b of 2 pi y times the square root of 1 plus dy dx squared dx. Now, I have this y circled because this is dependent on the axis that we are rotating about. If we're rotating about the y-axis, this becomes an x, okay? You have a dx over dy squared, and you have a dy, okay? So that's what changes. So, but we're rotating about the x-axis here, so that's what we're going to be working with, okay? So we'll just write a y here. Now, starting off here, we need to figure out what our dy dx is going to be, okay? So we need to find that. So we'll write over here dy dx is equal to what? We have a 9 minus x squared to the 1/2 as our y. So when we take the derivative, we'll have a 1/2 times 9 minus x squared to the negative 1/2. And it'll be times the derivative of the inside, which is negative 2x. Okay, and altogether, that's equal to, the 2's go away, and you're left with a negative x over the square root of 9 minus x squared. Okay, now, we need to square this. Okay, we need to square this because we have dy over dx squared on the inside. So let's square this. Let's get rid of this equal sign because now it's not going to be equal anymore. And we get that this is x squared over 9 minus x squared. Okay, and that right here is what we're going to be plugging in for our dy over dx squared. Okay, so let's do that. We get that our surface area, okay, our surface area is going to be equal to the integral from 0 to 2. Okay, those are our bounds. And that's going to be of 2 pi times y, which we're going to represent in terms of x because we're integrating with respect to x. We have a square root of 9 minus x squared. Then we have the square root of 1 plus dy dx squared, which is a x squared over 9 minus x squared dx. Okay, so now we can take out that 2 pi outside the integral, just to make this look a little prettier. And we have that 9 minus x squared inside that radical still. But for our next radical, well, this is the same thing as if we get common denominators here, we get a 9 minus x squared plus x squared over a 9 minus x squared. Okay, this minus x squared and the plus x squared go away, and you're left with a rad 9 over 9 over 9 minus x squared. Okay, and what you can do is you can just kind of get this radical out of here and just put it on the denominator and make this 9 a 3. Okay, just doing all these steps at once by like erasing and all that stuff here because I don't really want to write this out like 5 more times, okay, just for time's sake again. So we get rid of these 9 minus x squareds. Okay, they cancel out. So we get that our surface area is equal to 2 pi, the integral of from 0 to 2 of just 3, which is just going to be times 3x evaluated from 0 to 2. Okay, and well, the 0 kills that off, so we only need to worry about plugging in the 2, which gives us 2 pi times 6, which is 12 pi. Alright, so as long as you know which formula to use, okay, if you're rotating about the x-axis, you're using the one with y. If you're rotating about the y-axis, then your bounds are with respect to y, okay? You have a dy here, an x here, and you have dx over dy, okay? So, yeah, just that really is the only hard part about what we just did. I mean, to get this to simplify down, usually how it ends up working, at least in like half of the problems, is that you have to get common denominators inside the radical, and then you get something nice where the this y right here will cancel off with that dy over dx squared, or something like that will happen. Alright, so next we want to graph the parametric equations x equals t squared and y equals t plus 1. Okay, now how do we start off with this? Draw a txy table. Okay, the txy table is just the easiest way to go about this. Okay, now it doesn't specify here, it might specify on your test, it most likely will, but what I'm going to do is just do this from -3 to +3. All right, and we will just figure out what our x's and y's are going to be. So when t equals -3, what's your x? Well, your x, when you plug in -3 for t, you get 9. Okay, and that'll be the same for +3. Okay, and of course you can just kind of fill the rest in. When you have a -2, okay, this will be 4. You'll have a 4 down here. When it's 1, you'll get 1s here and here. When it's 0, you'll get a 0. Now what about with y? Well, this is just t plus 1. So you're going to have -2, -1, 0, 1, 2, 3, 4. And now you have your xy pairs. Okay? So you're inputting the parameter. Okay, this is your input column. And then you're outputting an xy pair. So let's graph that. Okay? You are starting out with a 9, -2. So let's go out 9 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, you're going down 2. So first point's going to be right here. Okay, now next you have a 4, -1. So 1, 2, 3, 4, -1. Next you have a 1, 0. So just right here. Okay, next you have a 0, 1. Right here. Okay, you have a 1, 2. Okay, that's going to be 1, 2. Next you have a 4, 3. Okay, so this will be a 1, 2, 3, 4, 1, 2, 3. And then lastly you have a 9, 4. So you're going to go up another tick, and you have right up here your 9, 4. Okay, so now you can trace this. Okay, tracing this. Oh, hopefully I don't mess up here. Ooh, got it. And let me get to that last dot. There we go. Man, that still looks pretty ugly. All right, well, do a better job than I did. That's my first recommendation. Okay, I just have the inability to be able to draw. I just made it worse. And well, here this is t equals -3, right? And this is t equals -2. So as t increases, we're going this way. Okay? So if we need to give this graph a direction, and it's of course going to be in the direction that t increases. Okay? That's how you figure it out. That's how you figure out your direction. Well, this was my t equals -3 dot. This was my t equals -2 dot. It's increasing this way, so my arrows are going to go around this way. Okay? Now, next we want to find the second derivative of our set of parametric equations here, x equals t squared plus 1, and y equals t squared plus t. Okay? Now, this is not something that you don't have to memorize the formula for your second derivative. Okay? You don't. What you need to know is that dy over dx, of course, I mean, this isn't something that you have to know. It's something good to know, but you don't have to know it. Okay? You can easily set this up because if you flip this, you get dy over dt times dt over dx. Your dt's cancel off, and you're left with dy over dx. So it makes sense. Okay? It makes sense for this to happen. Okay? And you can see more about that in the actual video, the explanation video that I did for derivatives with parametric. But anyways, what is going to be our dy over dt? We need to take a derivative with respect to t over here. Okay? And that will be a 2t plus 1. Next, we need to take a derivative with respect to t of our x equation, and that will just be 2t. Okay? And, well, that is the same thing as 1 over 1 plus 1 over 2t. Okay? We can split that up to say that. So that's your first derivative. But we need to find the second derivative, and to find the second derivative, okay, remember, you can't just square this and square this. That's not how it works. Okay? What you need to do is, wrong side again, take the derivative with respect to time of dy dx and put that over dx dt. Okay? Now this also makes sense. This is something I definitely covered again in the explanation video for derivatives with parametric, which is all these for all these problems. I'm going to have a video that you could reference to. I'll put that in the description. Kind of a little late to say that because we're on problem 14, but yeah. So dy dx. Now that's this piece, so that's going to go right here. Okay, so this is equal to the derivative with respect to time of 1 plus 1 over 2t. And then we're going to put that over dx dt, which is 2t. Taking that derivative, well, really, we only need to worry about the derivative of 1 over 2t because the derivative of 1 is 0. So if we take this derivative here, what we're going to get is, well, this is a 1/2 times this is t to the negative 1, so this becomes a negative t to the negative 2, okay, which is the same thing as negative 1 over t squared. Put that over 2t. And then simplifying this down, okay, you get that this is equal to negative 1 over 4t cubed. And right there is your second derivative, okay? So from that second derivative, now you're able to see, okay, where's this going to be concave up? Where's this going to be concave down? And that may be a question that you're asked. Okay, that definitely would make sense for them to say, okay, where's this going to be concave up? Where's this going to be concave down? Find the points of inflection, something like that. Okay. Okay, so now we want to find the arc length of x equals cosine t, y equals sine t, from 0 to 2 pi. Okay, now for this question, here's your formula. Okay, and this is another formula you don't necessarily need to memorize. Okay, as long as you know the arc length formula for just regular Cartesian, no parameter or anything like that, you're fine. Okay, because you can derive this, and I did more about that in the explanation video for this. Okay, but you know, this is probably easier to memorize it, but you can always derive it if you forget this equation. Okay. So all hope is not lost. Now we're integrating from 0 to 2 pi here. Okay, that's what this is saying. And dx dt, well, dx dt is, that's going to be negative sine of t. Okay, so I'll actually write that right here. Dx dt is going to be negative sine of t. So dx dt squared is going to be sine squared t. Okay, and dy dt is going to be cosine of t, so dy dt squared is going to be cosine squared t. Okay, so now you have what you need to put in to this formula already done, so you don't need to write this formula a bunch of different times. Okay, so on the inside you have a sine squared of t plus cosine squared of t, and you have dt on the end. This whole radical is 1, that's our identity, so really you just have the integral from 0 to pi, 2 pi of dt, which equals t evaluated from 0 to 2 pi, which equals 2 pi. Alright, now what is this, I mean, if you figure, and the arc length of your unit circle, because that's what the parametric equations of this are for, okay, this is your unit circle. Your unit circle has a radius of 1, and we know that the circumference is 2 pi r. Well, the radius is 1, so your circumference is just 2 pi. So we found this out with calculus now. For our next question, we want to graph r equals cosine of 2 theta. Okay, so graphing polar. Now the first thing we want to do is view r and theta as if they were Cartesian coordinates. Okay, so we're gonna have r on our y-axis and theta on our x-axis. Okay, now what is r gonna range between? Well, it's gonna range between 1 and negative 1, right? Cosine of 2 theta is not going to end up being any smaller than negative 1 and any larger than 1. So now we need to figure out what's going to happen with our theta axis here. Okay, what are going to be our individual tick marks here? Well, to do that, well, of course we know we're going to start off at 1, right? With cosine we start off at 1. But when are we going to get to 0? And that's what our little interval between tick marks is going to be. So we need to figure out when does cosine of anything equal 0. And that's, well, the soonest is when you get pi over 2, okay? So you want 2 theta to equal pi over 2, and if you divide by 2 on each side, you get theta equals pi over 4. So that's going to be your next tick mark. All right, so here we're going to write pi over 4, and then pi over 2, and 3 pi over 4, pi, and we can keep going a little bit here. Let's go to 2 pi here. We can write 5 pi over 4, and then this will be 3 pi over 2, and then we have 7 pi over 4, and 2 pi. Okay, so we start off at 1, we go down to pi over 4, we go over to pi over 2, up to 3 pi over 4, and then further up to pi, and then we're just going to repeat that cycle. Okay, so now that we have r and theta graphed as Cartesian coordinates, we can transfer that over to a polar graph. Right? And I know with a polar graph we just have this polar axis, which is the positive x-axis, but I'm going to kind of just use these 2 lines here as kind of like guidelines. I mean, they really help, so I'm going to keep them in. Now, we're starting at, well, theta equals 0 and r equals 1. So we're starting right here. Right? So we go from, as we go to our angle of pi over 4, which our angle of pi over 4 is right here, okay, we're going to go to 0. Okay? So what that's going to look like is this. Okay? So you can see that we're starting off really quickly decreasing, and then, we're starting off decreasing pretty slowly, and then we're increasing rapidly as we get to pi over 4. Okay, that's why this curve looks exactly like this. Now, as we go to pi over 2, okay, we're going in the negative direction now to -1. So what this ends up looking like is this. Okay, next we're going again, we're in negative r, we're going from pi over 2 to 3 pi over 4. So what this looks like is this. Okay, and you can just keep following this pattern, honestly. Okay, once you get the hang of what this graph will look like, you can just kind of keep going. Right, and right there you have it. Okay, that is r equals cosine of 2 theta. All right. Now for our next problem here, we want to find the slope of the tangent line for r equals cosine of 2 theta again, but at theta equals pi over 4. Okay, and here's your equation. Here's your d. Now this is something, okay, if you don't remember it, that's not a big deal, okay? This is something that we figured out in the explanation video for derivatives with polar. So again, that'll be linked in the description if you want to check that out. Okay, so now what we need to do is we have 4 things to solve for here. Okay, we have dr d theta, we have r, we have cosine theta, and we have sine theta. Okay, now r, we know that's cosine of 2 theta, but plug in pi over 4. Okay, when you plug in pi over 4, you get cosine of pi over 2, which is 0. For dr d theta, that's the derivative, okay, of this. So that's -2 sine of 2 theta. When you plug in a pi over 4 for your theta, you get you're going to get a pi over 2, right? Same as before. And now you have sine of pi over 2, which is 1. 1 times -2 is -2. Cosine of theta, cosine of pi over 4 is rad 2 over 2, and sine of pi over 4 is rad 2 over 2 as well. So now you have everything that you need to plug in. Okay, we now get that dy dx is going to be equal to, well, we don't even need to worry about these r parts. We don't need to worry about the second part here, because we know that this r is just 0. So it's going to cancel off that whole term. Now, dr d theta, we know that's -2, times sine of theta, that's rad 2 over 2. That's going to be over dr d theta, which is -2. Cosine of theta is rad 2 over 2. Okay, and obviously that is going to be equal to 1, which is your answer. All right, so really, nothing too difficult right there, as long as you know this formula, okay? And if you don't, as I said before, you can actually derive it. Now next, we want to find the area bounded by r equals cosine of theta from 0 to pi over 2, okay? And when I said, no, this is 0 to theta, okay? Theta is between 0 and pi over 2. There we go. Messed up. So what we need to know here is that when we integrate with polar, our area is equal to the integral from a to b of 1/2 r squared d theta. Okay, that is what we need to know before we start off. Okay, if you know that, then this problem becomes pretty easy. Okay, this problem will become pretty easy. You just have that your area, you're going to integrate from 0 to pi over 2, and you have a 1/2 times what's your r? Your r is cosine theta, squared is cosine squared theta, and then you have d theta. Okay, so you can use your half angle identity, simplify this down. You can pull out a 1/2 that you get from the half angle identity, and you have a 1/2 here. That makes 1/4, and on the inside you're left with a 1 plus cosine of 2 theta. Okay, so I use the half angle identity here to get 1 plus cosine of 2 theta over 2, and that over 2 I took out with this 1/2 to get 1/4 on the outside. Okay, so now we have a 1/4. We can integrate this to get a theta plus sine of 2 theta over 2, and that's going to be evaluated from 0 to 2, not 2 pi, pi over 2. And now we can evaluate. So we get 1/4 times pi over 2 plus sine of 2 times pi over 2 is just pi. Sine of pi is 0, so we don't need to worry about anything there. So we'll have pi over 2 minus the next term, which is going to be 0 plus sine of 0 is again, it's going to be 0. So really all we have is a pi over 2 here. So we have 1/4 times pi over 2, which is going to give us pi over 8. Alright, so again, just really knowing a formula here, and that's basically it. Alright, so if you were to get any kind of problem with sequences here, this is kind of what I would expect you to see, okay? It would be kind of testing your knowledge on just everything about sequences. So, is the sequence increasing or decreasing? Is it monotonic or not monotonic? Is it bounded? Is it convergent or divergent? Basically, it's just going to ask you everything about this sequence, and our sequence here is 1 over 2n plus 5. So let's answer the first question. Is it increasing or decreasing? Well, we can check that by figuring out what a sub n plus 1 is. Okay, a sub n plus 1 means we're just going to plugging in n plus 1 for n. If we do that, we have 1 over a 2 times n plus 1 plus 5. Okay, distributing that 2 through, we get a 1 over 2n plus 2 plus 5, which is going to be a 1 over 2n plus 7. So now, if we look at 1 over 2n plus 5, in comparison to 1 over 2n plus 7, we realize that this denominator is smaller, so the fraction is bigger. Okay, so a sub n is greater than a sub n plus 1, which means that this is strictly decreasing. And now we can move on to the next question. Is this monotonic or is it not monotonic? Now what does that mean? What does monotonic mean? Well, a sequence is said to be monotonic if it is strictly increasing or strictly decreasing. Okay? So something like sine, okay, where it's just going back and forth, is not going to be monotonic because it's not strictly increasing or strictly decreasing, it's doing both. So here we just have something that is strictly decreasing. So it is monotonic. Next we're asked, is it bounded? Okay, is the sequence bounded? Well, let's look at kind of what this would look like. Now, it's going to model something like 1 over n. Alright, you can basically say that. Okay, it's going to look something like 1 over n. So what you'll have is something like this. Okay, that may not be exactly what it looks like, okay, but it's going to be along those lines, okay, because you have something that looks like 1 over n. So you can kind of see here that you're going to have, it's going to be bounded on the bottom. You can definitely see that. But since it's strictly decreasing, it's also going to be bounded on the top. Okay, so that means it is bounded. Now what is it bounded by? Well, here, of course, it's bounded on the bottom by 0. But what is this top bound? Well, it's actually going to be where this point is, the first point, and the first point is where n equals 1. So where does, if we have our sequence here, 1 over 2n plus 5, if we plug in a 1 for n, if we plug in a 1 for n, we will actually get what that a sub n will be. Okay, so here we go. A sub 1 equals 1 over 2 times 1 is 2, plus 5 is 7. So a sub 1 equals 1/7, and that is your top bound. So it's bounded by 1/7 and 0. So you can say bounded. So 0 is less than a sub n is less than or equal to 1/7. All right. Now, lastly, is this convergent or divergent? Okay. Now, normally you could take the limit as n approaches infinity. Okay. You could take the limit as n approaches infinity of your a sub n and then see if it's going to converge to anything or it's going to diverge. And you still could do that here. But here's something we do know. It's monotonic. Okay. It's monotonic and it's bounded, which means that it's going to be convergent by the monotonic sequence theorem. Okay, so just a quick recap of the monotonic sequence theorem. It says that if you have a sequence that is monotonic and bounded, it will be convergent, and it's going to be convergent by the monotonic sequence theorem. Okay. Alright, so question 20 says, given the nth partial sum for the series the sum from n equals 1 to infinity of a sub n, will the series be convergent or divergent, and if it's convergent, find the sum. Okay, so you're given your nth partial sum here. Now, with sequences, we graph a sub n versus n. But with series, we graph s sub n versus n. Okay, so we graph our partial sums. So instead of taking the limit as n approaches infinity of a sub n, which we would do for sequences to see if it converges or diverges, for series, we take the limit as n approaches infinity of s sub n. And s sub n is right here. That's that 6n squared plus 7n plus 2 all over 4n squared plus 2n minus 85. Okay? Now, if you want to do this the hard way, divide everything by n squared or use L'Hopital. You don't have to do that though. Okay, we don't need to worry about the 7n or the 2. Okay, we want to worry about the highest power of n. Okay, we want to worry about the highest power of n here and the coefficients on those. We have an n squared on the top and bottom, and the coefficients in is a 6 and a 4. So simplifying that, that's 3/2, and that's what the limit will equal. So it's convergent. Okay, so that's another thing you can write. It's convergent, and the sum is the product of that limit, which is 3/2. So for question 21, we want to see if the series below is absolutely convergent, conditionally convergent, or divergent, and our series is the sum from n equals 1 to infinity of 5n squared plus 7n plus 4 over 3n squared plus 2n plus 1. And remember, for our series, for trying to see if they converge or diverge, we should be using the acronym DICLAR. Okay? Now that's for those of you that are new, that's the acronym that I use. It's kind of like my checklist for the series tests, okay? And I do it in this order. So I check for the test for divergence first, the integral test, the comparison test, the limit comparison test, alternating series, ratio, and then lastly, the root test, okay? So firstly, well, of course, we have the first part of the D, okay? That's the divergence test. So let's try the divergence test for this. We take the limit as n approaches infinity of our a sub n, okay, which is 5n squared plus 7n plus 4, over 3n squared plus 2n plus 1. And of course, just as we did the limit for the last example, we're going to do the limit here, and by looking at the n squared coefficients, which is just 5 over 3, that will be the product of our limit. And what the test for divergence tells us is that if the product of our limit is not equal to 0, which it's not here, then the series is divergent by the test for divergence. And my recommendation, of course, if you're following this checklist, it works out, okay? But definitely always try the test for divergence first, unless you have something like a factorial, or something that it's obviously going to be a ratio test, or it's obviously going to be some other test. I would go straight to that test. But really, if it's a series that you're not too sure about, always start off with the test for divergence. Next, we want to again see if the series below is absolutely convergent, conditionally convergent, or divergent, and we have the sum from n equals 1 to infinity of 2 over 6n minus 1. Now here, let's do our series tests, okay? First off, we have the test for divergence. Will we be able to do that here? We can, but the limit's going to equal 0. So the test for divergence is not going to help us. What about the integral test? Well, actually, that seems like it could work here. Okay, this is going to be something that's easily able to be integrated. Okay, we can write this as 2, the sum from n equals 1 to infinity of 1 over 6n minus 1, and that's something we can easily integrate. Okay, so let's do that. We're going to compare this to the function, let's go f of x equals the integral from 1 to infinity, okay, 1 to infinity, n equals 1 to infinity, of 1 over 6x minus 1 dx. Now to make sure that we can do this, what we need to do is make sure that this function is going to be positive, continuous, and decreasing along this interval from 1 to infinity. Okay, so first, let's check if it's positive. Well, of course, every term here, you're going to see that every term will be positive. Okay, or and whatever you plug in for x, you're going to get something positive. Okay, it's all positive. So that's going to work. Is it continuous? Well, you're not going to see, there's no way you can get any kind of discontinuity here, okay, from 1 to infinity, that is. So it's going to be continuous. Now, is it decreasing? Well, it's actually going to be easier to see if this n equals 1 to infinity, the a sub n here, if that's going to be decreasing. You can look at the next term in the series by plugging in n plus 1 for n. And when you do that, you get 6 times n plus 1 minus 1, which is equal to 1 over 6n plus 6 minus 1, which is 6n plus 5. You can see that this denominator is much bigger than this one, so this fraction will be greater than this one, which means that it is indeed decreasing. So now that you've passed your conditions, you can actually go about integrating this. Okay, so if you're going to integrate this, I'll bring it over here. You have to take the limit as t approaches infinity because you cannot have an infinity as a bound. So you have to have a quantity that approaches infinity. So you take the limit as t approaches infinity of the integral of 1 to t of 1 over 6x minus 1 dx. Okay, this is just a u substitution. You can set u equal to 6x minus 1 and du equal to 6 dx. Divide by 6 on both sides, and there you go. Now you have to fix your bounds, put it in terms of u. If x equals 1, then what will u equal? Well, it's going to be 6 minus 1, which is 5, and when x equals t, u, doesn't matter that you're multiplying by 6, it doesn't matter that you're subtracting 1, u is going to equal t. Okay, the only time it would matter is if it was something like u equals 1 over x, okay, which would be a weird substitution, but if you had to do something like that, u equals 1 over x, well then you have 1 over t, which is going to be 0. So that's the only time that something like that would matter. So kind of just substituting in here, we get the limit as t approaches infinity, the integral from 5 to t of, this is going to be, we're going to bring out this 1 over 6, and we have a du over u. Okay, which gives us the limit as t approaches infinity of 1/6 the natural log absolute value of u from 5 to t. And evaluating that, you get the limit as t approaches infinity of 1/6 times the natural log of t minus natural log of 5. And you can see that that is going to be divergent by the test for divergence. Okay, or sorry, not by the test for divergence. What am I thinking? This is going to be divergent by the integral test. And why it's going to be divergent is because this integral right here will be divergent. Okay, when you have that natural log of t as t approaches infinity, you'll get an infinitely large number here. Okay, so since that equals infinity, since your integral diverges, your series will diverge as well. That's what the integral test tells you. All right, so number 23, we're again asking absolute convergence, conditional convergence, or divergence for now the series from n equals 2 to infinity of 2 over the natural log of n. Now here, if you use the test for divergence, you'll get that it's equal to 0. So that fails, okay? The integral test, you're not going to be able to do anything with that here, so that fails. Comparison test, well, possibly. You can't really rule out that possibility. And you can't really rule out limit comparison test either. Alternating series, no, this isn't an alternating series. And ratio and root, root will definitely not work. And ratio, I don't really see how that's going to help here. So that's going to be a no. Now it's okay to leave question marks like that. Maybe comparison test will work. But I'm going to reserve that, for later. That's going to be like the last case scenario, or the worst case scenario, if maybe some of these other tests won't work a little bit better. Okay, so here, let's try using a comparison, okay? Because we already know that none of the other tests are going to work. Maybe limit comparison, but we need to check comparison first. Okay, well, first we can rewrite this as 2, the sum from n equals 1 to infinity of 1 over natural log of n. Okay, that's something we can do. That's going to make the comparison a little bit clearer. So what are we going to compare 1 over natural log of n to? And I've done this before in another video, because this is an extremely hard comparison to really kind of see. I mean, it's not as intuitive. That's why I say it's hard. But you want to compare this to actually just 1 over n. Okay? Why do you want to compare it to 1 over n? Well, 1 over natural log of n is actually going to be greater than 1 over n, because natural log of n is less than n. Okay? For any n. For any n on this interval, at least. And this should be an n equals 2, because we can't have a natural log of 1. Okay, so what this tells us, since we know that the sum from n equals 2 to infinity of 1 over n diverges, okay, that means that this series is going to diverge as well by the comparison test. So here's kind of a nice written out answer explaining kind of the whole deal here. So since the series, the sum from n equals 2 to infinity of 1 over n diverges, okay, since it diverges, and that 1 over n is less than 1 over natural log of n, we know that this series, the sum from n equals 2 to infinity of 2 over natural log of n, will diverge by the comparison test. Okay? So that's kind of the idea. If 1 over n diverges, if it diverges and there's something greater than that, of course it's going to diverge as well. Okay? It never really has the chance to be convergent. Alright, so for our next problem here, again, absolute convergence, conditional convergence, or divergence. But now for the sum from n equals 2 to infinity of 1 over n cubed minus 1. Okay, now this you can use to test for divergence, not going to work. Okay, the limit's going to equal 0, so you got to move on. Integral test, not going to work. Comparison though, maybe that'll work. Okay, let's try a comparison here. Let's compare 1 over natural log, or sorry, I'm still on the last problem. 1 over n cubed minus 1 to 1 over n cubed. What's the comparison there? Well, 1 over n cubed, right, this denominator n cubed is going to be greater than n cubed minus 1. So 1 over n cubed is actually going to be less than 1 over n cubed minus 1. Now that's a problem, because we know that 1 over n cubed converges. So 1 over n cubed would have to be greater than 1 over n cubed minus 1, and it's not. So what we have to do is use the limit comparison test. Okay? So basically, our series, okay, our series is the a sub n, the 1 over n cubed minus 1. And the compared series is b sub n. And what the limit comparison test is telling us is that we need to take the limit as n approaches infinity of a sub n over b sub n. Okay, that's the first step. We'll worry about the other stuff later. So we do that. We take the limit as n approaches infinity. In a sub n, that's 1 over n cubed minus 1. So let's write that down. And we're putting that over 1 over n cubed. And making this look a little bit nicer, we get the limit as n approaches infinity of n cubed over n cubed minus 1. And of course, you can see that this limit is going to equal 1. Okay, the limit's going to equal 1. 1 is greater than 0, which is one of the conditions of the limit comparison test. Okay, it needs to be greater than 0, and it needs to be finite. Now, if the product of your limit, which ours is 1, if it passes both of those conditions, which it does here, then what that means is either both the series are going to converge or both the series are going to diverge. Okay? What that means is that by the limit comparison test, this series is going to converge, and the reason for that is because the series from n equals 2 to infinity of 1 over n cubed will converge. Okay? Now remember, we're wondering about conditional convergence or absolute convergence. Okay? But you can see here that it doesn't matter if you take an absolute value here. Okay? This is still going to be the exact same thing. Okay? You're always going to get positive terms. So the absolute value does nothing for you. And what that means is that this is actually going to be absolutely convergent. So you can say, right, convergent by the limit comparison test, and then you can say, I drew a line through this because I'm so tired at this point, absolutely convergent because it is convergent and all of your terms are positive. Okay, so that's how you can kind of explain how it's absolutely convergent as well. Okay, so for our next problem, we again want to see if the series is going to be absolutely convergent, conditionally convergent, or divergent. And our series now is the sum from n equals 1 to infinity of negative 1 to the n minus 1 times n squared over n cubed plus 2. Now here, we could do test for divergence, not going to work. Integral test and comparison test, limit comparison, not going to work here. Okay? Need positive terms anyway, and we don't have positive terms. We have that negative 1 to the n minus 1. So we're going to have to do an alternating series test. Let's work with that. So what the alternating series test tells us, okay, first we need to figure out what our b sub n is going to be. Okay, this is our a sub n. We need to find our b sub n. And our b sub n is just going to be the a sub n, but taking out whatever makes the a sub n alternate, which is that negative 1 to the n minus 1. So our b sub n is just going to be n squared over n cubed plus 2. Now what we have to do is see if this is decreasing, and then if it is, let's take the limit as n approaches infinity and see if that's going to equal 0. If it is, then we know that this is convergent by the alternating series test. So first, let's see if this is decreasing. Let's see what b sub n plus 1 is going to be. B sub n plus 1 is just going to be a n plus 1 quantity squared over n plus 1 quantity cubed plus 2. Okay, now we don't really need to distribute this or to FOIL this out and do like a big expansion here, because you can kind of just like think about this logically. Okay, this is obviously going to be smaller than this. The reason why is because your denominator is being raised to the third power. So if you add 1 to n, okay, and then you cube that, it's going to make a lot more difference here than it will here, because n plus 1 is being not cubed, it's being squared. Okay, so there's going to be a bigger difference on the bottom, so your bottom is going to be bigger, and that means that your whole fraction will be smaller. Okay, so b sub n is greater than b sub n plus 1. Okay, so just think about that logically. Now, next we need to see the limit as n approaches infinity of b sub n. The limit as n approaches infinity of n squared over n cubed plus 2. Now, will that equal 0? Well, yes, because the highest power of n is on the bottom and it's not on the top, so it's going to equal 0. All right? So that's the other part. Okay, the limit equals 0. So that is check mark, check mark. It's convergent by the alternating series test. Now remember, okay, and I've done this before where I've just figured out if it was convergent or divergent and left it. Okay, I actually got points off for that. I was really mad. But you want to see if it's absolutely convergent or conditionally convergent. So what you need to do is take the absolute value of your a sub n. Okay, so let's do that down here. We have the sum from n equals 1 to infinity of negative 1 to the n minus 1, n squared over n cubed plus 2, and we can take the absolute value of it, which means we're just going to drop the negative 1 to the n minus 1, and be left with the sum from n equals 1 to infinity of n squared over n cubed plus 2. Okay, so now what you need is another round of Maclaurin. Okay, so it's basically like 2 problems in one. Now, looking at this, the test for divergence, the limit will equal 0. What about the integral test? The integral test actually might work here. Okay, so we can compare this to the integral from 1 to infinity of, we can say that this is x squared over x cubed plus 2. Now looking at this, is it going to be positive, continuous, and decreasing on the interval? First off, all the terms are positive, so yes, it's going to be positive. Not going to be discontinuous anywhere, so it will be continuous. And is it decreasing? Okay. Well, it's actually going to be easier to see if it's decreasing from the n's here. We can look at n squared over n cubed plus 2 versus n plus 1 squared over n plus 1 cubed plus 2. But we just did that. Okay, we just did that up here. So we already know that, yes, it's going to be decreasing. And that passes our 3 conditions. So we can actually take this integral. Okay, so let's do that. We get the limit as t approaches infinity, because we can't have infinity as a bound. The integral from 1 to t of, we have an x squared over x cubed plus 2 dx. Okay, we need a u sub. Okay, we need a u sub. So our u is going to equal x cubed plus 2. Our du is going to equal 3x squared dx. And we're going to need to divide off that 3. And we need to also do our bounds. When x equals 1, u will equal 3. When x equals t, u will equal t. Okay, so there's all that. So now, let's go back over here. We now have the limit as t approaches infinity, the integral from 3 to t of, well, this is a du over 3 now, so we're going to plot a 1/3. And we have a 1 over u. So we'll just have 1 over u du, which is going to give us the limit as t approaches infinity of 1/3 natural log absolute value of u from 3 to t. Okay, and if I don't really have too much room, so I'm just going to do this here. Natural log of t minus natural log of 3. You can see that it's going to be divergent because you have that natural log of t and t is approaching infinity. Okay, so since that's happening, that means that this is conditionally convergent because this is divergent by the integral test. And I wouldn't abbreviate these as IT and AST and things like that on the test. I would just write it out so you don't get points off because you have like a strict teacher or something like that. But yeah, so this is conditionally convergent. Why is it conditionally convergent and not absolutely convergent? Well, that's because it was convergent just by the alternating series test. The regular series was, but when we take the absolute value, it was divergent, and that's what means conditional convergence, okay? If it was convergent here, then it would be absolutely convergent. Alright, so next, again, we want to see if the series is going to be absolutely convergent, conditionally convergent, or divergent. And our series now is the sum from n equals 1 to infinity of -1 to the n plus 1 times n to the 4th times 4 to the n over n factorial. Okay, so you see the factorial there, okay, and what you need to be immediately thinking is, no, I can't do any test but the ratio test. Okay, it has to be the ratio test. You cannot do anything else. You need to go to the ratio test. That's it. So the ratio test tells us that when you take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so let's do that here. We get the limit as n approaches infinity of the absolute value of. Now, this is going to be really messy at first. We have the a sub n plus 1. Let's plug in an n plus 1 wherever we see an n. Now, before we do that, this absolute value is just going to get rid of this -1 anyway. So really, there's no sense in doing extra work. Let's just forget about that -1. So here we have a n plus 1 to the 4th power times a 4 to the n plus 1, and that's going to be over a n plus 1 factorial. This will all be over n to the 4th times 4 to the n over n factorial. Okay, so now we can clean this up. We'll get the limit as n approaches infinity of the absolute value of a n plus 1 to the 4th power over n to the 4th times a 4 to the n plus 1 over 4 to the n. And that's going to be multiplied now by an n factorial over n plus 1 factorial. Okay, so the limit rules say we can take the limit of each of these things independently, and also before we even do that, you can kind of see how I grouped each of these things that we took the a sub n plus 1 of and their counterpart when we did the a sub n. I grouped them together because you're going to see a lot of really nice cancellations. Okay, and it's really nice to see that when you group it this way. So we take the limit as n approaches infinity of, well, actually, what are we going to have here? I don't actually, yeah, we should do this. Okay. This first piece right here, you could actually just look at it and tell me the limit of it, okay? We have an n to the 4th over n plus 1 quantity to the 4th. And when we do our expansion here, you're going to see that what will the first term be? It's going to be n to the 4th, okay? So nothing else matters, just that n to the 4th. And the coefficient on that is going to be 1. The coefficient on the bottom, n to the 4th, is 1. So really the limit of that is just going to be 1. Okay? Now 4 to the n plus 1 over 4 to the n. Well, when you divide this out, you subtract the exponents and you just get 4. And for this n factorial over n plus 1 factorial, remember that n plus 1 factorial is the same thing as n plus 1 times n factorial, and the n factorials cancel out and you're left with 1 over n plus 1. So really you just have the limit as n approaches infinity of the absolute value of 4 over n plus 1. Now, as n approaches infinity, your denominator will get infinitely large, and that means that this will go to 0. 0 is less than 1, okay? Because remember, with the ratio test, we compare this to 1. If it's less than 1, it's absolutely convergent. If it's equal to 1, it's inconclusive. And if it's greater than 1, well, then it's going to be divergent. But here it's less than 1, so that's absolutely convergent by the ratio test. And one thing, one little piece of advice, whenever, whenever we had a really, really tough series or anything like that, my TA at the time would say, when in doubt, ratio test. And really, that's pretty much what you should be doing. I mean, when in doubt, ratio test. If the ratio test doesn't work, then, maybe move on to something else. But if you're faced with something really hard, chances are the ratio test will do some damage to it. All right, so here, again, proving absolute convergence, conditional convergence, or divergence. But now for the sum from n equals 1 to infinity of 3n cubed plus 1 raised to the nth power over 6n to the 4th minus 2 raised to the nth power. Now here, put a big check mark next to the root test. That's your go-to, okay? This is kind of like seeing a factorial on a series and going right to ratio test. If you see everything to the nth power, okay, because you can rewrite this by taking apart like this, and then putting everything to the nth power. It's the same thing, okay? When you see something like that, root test that all day, okay? So when we do the root test is telling us to take the limit as n approaches infinity of the nth root of the absolute value of a sub n. So let's go ahead and do that here. Take the limit as n approaches infinity of the nth root of the absolute value of 3n cubed plus 1 over 6n to the 4th minus 2. And that's all raised to the n. Forgot to put that in. Alright, whatever. And the nth power cancels out with the nth root, and you're left with the limit as n approaches infinity. We don't need the absolute value signs here. Okay, that's not going to change anything. You get 3n cubed plus 1 over 6n to the 4th minus 2. Now you know that this limit is going to equal 0. Okay, your highest power of n is on the bottom. 0 is less than 1, and so this is absolutely convergent by the root test. Okay, the root test is pretty obvious when you need to use it, okay? It'll literally is only useful for something like this. So, and if it fails, if it's inconclusive and you have something like this, test for divergence, okay? The test for divergence will most likely prove it to be divergent. That's usually what's happened to me, at least, so I definitely will pass that on to you and say, yeah, go test for divergence. Alright, so for this next problem here, we want to see if the series is just convergent or divergent. We have the sum from n equals 1 to infinity of cosine of n over n squared. Now here, this series is a little interesting. You're not going to be able to prove it with anything with Diclar, okay? Because here's the idea. If you start listing off terms for this series, okay, you get cosine of 1, and I'm just going to talk about the numerator here, cosine of 2, cosine of 3, cosine of 4, and let's go cosine of 5 and cosine of 6. And, well, cosine of 1, and you can look at this for yourself. Remember, these are in radians, okay? So cosine of 1, that's in the first quadrant, that's going to be positive. Cosine of 2, that is going to be in the second quadrant, and that's negative. Cosine of 3, that's in the second quadrant, negative. Cosine of 4, that's in the third quadrant, that's going to be negative. Cosine of 5, that should be in the fourth quadrant, and that's going to be positive. And cosine of 6 is in the fourth quadrant, and that's positive. So you see that the signs are not alternating, okay? And they're all positive or either all negative. So what this means is that you're going to have to prove absolute convergence. Okay, if you prove absolute convergence, then you can prove that this thing is convergent. Okay, so what we can do here is take the absolute value of this. Okay, let's take the absolute value. And actually, so we don't wreck the original series, I'm going to do that down here. Now, where does this absolute value actually apply? Well, the n squared is going to stay positive, but this cosine of n is what's alternating between negative and positive. Well, not alternating, it's just moving between negative and positive. Okay, so what is this absolute value doing for us? Well, that means that instead of being between negative 1 and 1, this cosine of n is just going to be between 0 and 1. Okay, so what that means is that we can compare this to 1 over n squared and know that cosine of n, the absolute value of it over n squared, is going to be less than or equal to 1 over n squared. Okay, and what that means is that this series is going to be convergent by the comparison test. If it is convergent by the comparison test, that means that we have absolute convergence. And if we have absolute convergence, that means it is therefore convergent. Okay, so there is an example of where absolute convergence really comes into play. Okay, so it's not something just useless that you learn. So last two problems here. All right, we have 29. Find the Maclaurin series for f of x equals x cubed times e to the negative 3x squared. Okay, so now how do we even go about doing this? Well, we don't need to start from scratch because we know the Maclaurin series for e to the x. Okay, and that's something that you should know. Okay, if you don't have it memorized, it's not the end of the world. You can start from scratch, find e to the x, and then find x cubed times e to the negative 3x squared. Okay, so it's not the end of the world if you can't memorize it. But this is x to the n over n factorial. Okay, I would definitely make sure that these are memorized though, because, I mean, listen, if you have to start from scratch, you're taking a lot of time. That may be 10 extra minutes or 15 extra minutes, you know, depending on how fast you are started from scratch with Maclaurin series. But, you know, that's a lot of extra time to be taking on a timed test. So, if we know that this is e to the x, well then we can figure out what e to the negative 3x squared is. We just plug in a negative 3x squared wherever we see an x. And that's going to give us negative 3x squared to the n over n factorial, which we can write to be a little bit nicer as the sum from n equals 0 to infinity of negative 3 to the n over, or not over, times x to the 2n over n factorial. And you can even take this out further and write it as negative 1 to the n times 3 to the n. It's up to you. Now we can go just our last step here, x cubed times e to the negative 3x squared. And that is going to be equal to the sum from n equals 0 to infinity of, now we're just going to multiply through that x cubed. Okay, and that can go inside the sigma. It's not dependent on n at all, so it doesn't really matter whether we have it inside or outside. But if we multiply it here, we add the exponents, okay, and we get 2n plus 3. So we just have a negative 3 to the n times x to the 2n plus 3, and that's going to be over n factorial. And right there, you have your Maclaurin series representing x cubed times e to the negative 3x squared. Okay, so moving on to the last problem. Last problem here, find the Taylor series for f of x equals 1 over x squared at a equals negative 1. Now, this is something that we're going to solve by starting out from scratch, okay? This doesn't match any of our templates really any of our common Maclaurin series that closely. So what we're going to have to do here is just start from scratch, okay? So in the case that you do have to start from scratch, you don't remember one of the power series, one of the Maclaurin series that are common, you know, here's how you kind of go about starting from scratch. So the first step is going to be to take derivatives of f of x and find the nth derivative of x, okay? So we have 1 over x squared here. We're going to write that as x to the negative 2, okay? Now f prime of x, that's going to be a negative 2 times ax to the negative 3. Now to make this a little obvious, more obvious, that there's a negative 1 here, okay, or a negative here, that's what I'm going to do. I'm going to put a negative 1 out here. Okay, just going to make things a little bit more obvious. Because remember, we're looking for a pattern here. And when I take the double derivative here, what happens is, well, I have this negative 3 come down and cancel out this negative 1. So right now I have basically a 3 times 2 times 1 times x to the negative 4th. Okay, when I take the third derivative, I end up with a, what do I have here? A negative 1 times 4 times 3 times 2 times 1 times x to the negative 5. And now you can kind of start to see the pattern. It starts to become really obvious. If I'm trying to find the nth derivative of f at x, what happens is, well, first off, we know that this f of x is our n equals 0 term, this is our n equals 1 term, this is n equals 2, this is n equals 3. Okay, that's how we figure out, because we see we have an alternating negative here. So we want to know if we need to put n or n plus 1 in the power. Okay, you see that the odd terms are the negative ones. So this is just going to be negative 1 to the n. Okay, now next, let's take care of this factorial that we see here. Here we see a 2 times 1. Here we see a 3 times 2 times 1. Here we see a 4 times 3 times 2 times 1. Okay, now you can kind of say that we have a 4 factorial on our third derivative, a 3 factorial on our second derivative, so it's always 1 more and then factorial. So for our nth derivative, it's going to be n plus 1 factorial. Okay, so lastly we have our x, okay, our x to a power. Now for our 0 derivative, okay, which is just f of x, we have negative 2. For our first derivative, negative 3. For our second derivative, negative 4. Okay, so it's always 2 greater, but in the negative direction. So how we write this? We can just put it on the bottom actually and get rid of the negative, and we can write it as x to the n plus 2. Okay, so now the second step, step number 2, is to plug in your x equals a. Okay, so plug in a for x, and our a is negative 1, as it says in the problem. So f of negative 1, that's going to just equal 1. F prime of negative 1 will equal 2. F double prime of negative 1 will equal 2 times 3. F triple prime of negative 1 will equal 2 times 3 times 4. Alright, and you can kind of see pretty much, what's going on here already. Okay, so if you have your nth derivative of f at negative 1, you will get your n plus 1 factorial still. That's not going to go away. Okay, you'll have on the bottom here, okay, you'll have a negative 1 to the n plus 2. Okay, you'll have a negative 1 to the n plus 2. Why will you have that? Well, the reason why you have that is because you're plugging in a negative 1 into your x. So what's happening here, and of course you have that negative 1 to the n as well. Okay, what's happening here is that this is for all odd terms, okay? And this is for all odd terms. So you have 2 negatives contributing on all odd terms. So really, this isn't going to matter at all. So all you're getting out of your nth derivative of f at negative 1 is literally that n plus 1 factorial, and that's it. So moving on to step 3, which is to just set up our series. Now we know the format for a Maclaurin series, or not a Maclaurin, we're on Taylor. For a Taylor series is the nth derivative of f at a, which in this case is negative 1, over n factorial times x minus a to the nth power. Now, we can plug in what we have here, this n plus 1 factorial, in for our nth derivative of f at negative 1, right? That's what we found. That's why we found it to plug it in here. And we put that over n factorial and we multiply it by x minus a to the nth power. Okay, well we know that n plus 1 factorial, that's the same thing as n plus 1 times n factorial. The n factorials cancel out, and you're left with that n plus 1 times x minus a to the nth power. And I forgot to substitute in here. We just get now, our a is negative 1. Okay, so we get x plus 1 to the nth power. Alright, so now that's really it. That's our series. The sum from n equals 0 to infinity of n plus 1 times x plus 1 to the nth power. Alright, so that is going to do it for our Calculus 2 final review. Alright, good luck on your exam. I really hope this helped. If you want some more review, remember I have that 100 question review video down in the description. Okay, it's like 2:30 in the morning right now, and I'm doing this for you guys. Alright, so if you want to consider supporting me on Patreon, I'm going to urge you. That was a little guilt trip right there. So, consider supporting me in the form of currency on there. And yeah, so good luck on the final exam. I hope you do well, and that's going to do it for this video.